Lloyd. Today I will continue to the Cosmology school note. The second and the third topic of the week one, which is the CMB and the implication. So I will explain these two topics together. So some order of the CMB and the implication lectures are mixed. So the CMB, especially the CMB, has the anisotropy over the inhomogeneous. So one can expand the CMB anisotropy, which is some temperature inhomogeneity over the multiple moment L. So for example, if L is a 2, this corresponds to the dipole, and the small r means that the 1 over epsilon is small, so the angular scale becomes large. And statistically, one can calculate the two-point correlation functions of this anisotropy, so that the CMB power spectrums can be obtained. And such anisotropy is coming from the primordial density perturbations and the transfer functions over the cosmic evolution. So usually the cosmologists consider the estimator CL hat as summations of the ALN with the normalization factor. And the variances of this estimate is proportional to the 1 over the root of the 12 plus 1. So the for small l, uncertainty becomes large because the angular scale is large. So the intuitively is that there are viewpoints to select the 2 point to get the statistical variance. But the small l, this L mode enters later because the scale is also large. So the enter the subhorizon is late. So the this moment might be after the recombination. So the this is only affected by the primordial no-late time evolution effect. Such a CMB appears at the recombination when the positrons and the electrons are trapped to the hydrogen atom around the 0.26 electron volt. This can be obtained by the recombinations around thermal equilibrium, some calculation, and this temperature is lower than the binding energy of the electron because the photon hit the electron, so the bond state requires the more cooling. And also one can define the optical depth to describe the scattering length of the last scattering, and by using this optical depth detail, the non-scattering probability PNS can be obtained, and this becomes exponential of the minus tau, as tau is the optical depth here. And by using that, one can define the function gz, which has a peak around the z becomes the 1000, so which is the moment for the recombination. And the next was continuing the CMB. To obtain the CMB anisotropy, one should know about the cosmic evolution, how the density perturbations evolve. For example, the capital Pi, the gravitational potential, and the matter power spectrum delta m's that evolves differently depending on the specific mode in the horizon. So this determines the horizon and sub-horizon, and depending on the universe era, like as radiation RD, matters MD, and darkness lambda D. So for the super-horizon case, gravitational potential is a constant, but in the sub-horizon case, during the RD, the gravitational potential is the oscillates and the decay. And for the sub-horizon case, the matter power spectrum grows as a logarithm, but MD, it grows as a linear scaling. So by using that, one can establish this the density perturbations of each quantities in each era. So these plots show that each moves for the RD and MD case. R is represented as RD and M represented as MD. And the Hubble horizon, Hubble inverse is increases over the cosmic history. So the over the Hubble inverse the came out in the super horizon, but below that the came out in the sub horizon. So continuing is that one. So one can consider the Hubble horizon, co-moving Hubble horizon evolutions to the, by adding the impulsion approach, and also one can establish the density perturbation in the ZR by considering the metric and the SVT. This already we talk about it. So just stop it discussing in the CMB part. Let's talk about the impulsion. So there's a various problem in the Big Bang standard cosmology. So the impulsion is necessary. So which is as the problems in the Big Bang? The first one is the horizon problem. Why the CMB is so isotropic? Almost the same temperature for different direction. Because information and light cones are only the causally connected, and we can evaluate the horizon size by integrating the component time eta. And the horizon is given by the 1 over AH is for the interval of the logarithms of the scaling factor. But this Hubble horizon just becomes 1 over A dot by the definitions of the Hubble constant. And by using the second Bradman equation up to, then the when the omega, the equation of the state is larger than the minus 1 of dot, then the A2 dot becomes a negative. So the A dot is a decreased. So the Hubble horizon size increases when the omega is larger than that value. So usually the RD and MD, this equation of the site is a 0 or the 1 of dot. So the this condition is satisfied. So the Hubble horizon size increases in the lifetime. So this is diagrams over the conformal time. There's observations in the current approach, another observations in the CMB at the decoupling moment of the photon. For the observer one, they can see these large regions inside the horizon, but the observation two, they can only observe this blue region. This region is only the causally connected. By considering these two difference, then the 10 to the minus 5 10 to the 5 causally disconnected patches, which is cannot provide sort of the same temperature. This is called the horizon problem. Maybe that there are pages error. Page 14 to the page 15 is unnecessary. Maybe the here. Yeah, this is the page 14 to the 15. So to resolve this horizon problem, we need the large causally connected in the past time of the cosmic history. This requires that the omega equation of the states becomes smaller than the minus 1 of dot in the very early approach. And this can also resolve the singularity problems simultaneously. So if we extend this the component time, then now the two different observers at the CMB, two light cones that overlap each other. This is can be possible by the prolonged access rate component time. The second problem of the Big Bang cosmology is the blindness problem. From the Bradman equations, the first one, F1, one can realize this form 1 over the omega, and this is just given by the proportional to the curvature term k. And then now again the 1 over the h is increases in the right hand side. But by the observation, we know that the omega is capital omega is almost 1, k is almost 0, the universe is almost flat. But the right hand side, this term increases, so the omega should be the more near to the 1, more fine-tuned. This is called the brightness problem, also related to the horizon size. So if the one of the IHs are decreased in a very early approach, then such a problems also can be solved simultaneously. So also there are some monopole problem. If we assume that the ground unification theory GUT, then there will be the symmetry breaking and the monopoles appear. And if the monopole dominates, then this is called the monopole problem, which is the integral of the cosmic history. So to resolve such a monopole problem, certain implications are required. Usually the implications model adopts the new scalar field, so-called inflaton, and this inflaton field lives in an expanding universe. So that we solve the actions, and this gives the following equation of motion by assumptions of the spatial homogeneity, and one can calculate the energy tensor and extracts the energy density law and the pressure P. And the omega as a lightest of the project of energy density should be smaller than minus 1 of 3. And this can be realized when the potential energy dominates over the kinetic energy. This is called the slow roll condition. Okay, now I'll turn back to the page 16, maybe around here. Page 16, yeah, here. So the slow roll conditions, again, the dominated potential energy. And one can define the slow roll parameter epsilon, which is hinges of the Hubble parameters, and this is just given by the kinetic energy over the some dimensional parameters by inserting the T plasmagnetic equation. So this slow roll parameters epsilon should be the smaller than the 1, and this is equivalent with the smaller equation of the size omega. And there is additional slow roll parameters eta, which is changes of the epsilon or changes of the pi dash small. This eta should be smaller than the 1 also, but the absolute value. And this epsilon and eta can be written by the epsilon v and eta v, which is purely determined by the shapes of the potential for the inflaton field. The slow roll conditions are almost similar. Epsilon is similar to epsilon v, and eta is the difference between the eta v and minus and the epsilon v. And also there's a new quantity conformal time, and it both the n as defined as the Hubble, dt, and the dRNI. And by using the implications and condition, when the slow roll from the epsilon becomes the 1, this n is related with the a initial, the a n of the implication, and can be written by the in terms of slow roll parameters, and this n should be larger than the 60 by the observation of the data. So, for example, as a simple example, one can consider the potential as the quadratic 1 polynomial. Then one can calculate the epsilon, and the result becomes a pi value. The field value should be the super Planckian. And one can also calculate the implications of the ending condition and the e-board, 6 e-board condition. And as a result, the potential shapes are extremely very flat. And this simple polynomial implications models excluded by the observations from the spectral index and the tensor to scalarity. So I will talk about them soon. How can we detect such implications theory or model? By the content fluctuation. The inflaton field has the fluctuations pi equal to the pi to the delta pi, and also for the tensor part matrix mu. So this is the Hubble horizons over the time, and we will use some case invariant quantity, tensor perturbations R, and we will choose the moving gases here. So the content fluctuations can be obtained by the second order of the inflatons and Einstein-Hilbert action. Then the equations are following. A lot of it is discussed in the cosmological perturbation series in the other video. And by the changes to the variable, the curvature perturbation R becomes the V, and the scale factors becomes the Z, new variable. Then the actions becomes such a form, and one can obtain the equation of the motion. So now we'll keep going through the implementations later, but again the CMB then order of the mixed here. So in the CMB also we talk about the density perturbation. We'll impose the adiabatic condition and the superhorizon limit. Then there is a relation between the curvature perturbation curly R and the gravitational potential psi. And this gravitational potential has a different values in the RT and MT with the 9 of the 10 factor. So we'll talk about how the CMB has the baryon acoustic oscillation signatures. This can be described by the baryon bottom fluid, a lot we discussed before. So there is a two anisotropy concept of the baryon and the radiation. And one can define the capital R, the factors, as the baryon and the photons one, and this will give the corrections on the speed of the sound. Then the equations of the motion for the set juice, the CMB anisotropy function has the following standard harmonic oscillation form, but slowly varying frequency. And from the speed of the sound CS, one can bound of the sound horizon RS, and the solutions of this equation has the following oscillating form. And the sine term becomes a zero by the initial condition, and the cosine term has a peak when the inside of the cosine potential becomes n pi, and the sound horizons are fixed at the recombination. So by using this relation, one can obtain the peak of the baryon acoustic oscillation. And for the first peak in the CMB post spectrum, this occurs in the 0.6 degree. And also there are the other effects for the CMB anisotropy, not only in the density perturbation, there is a gravitational potential effect, which is the Sachs-Fulton effect. Okay, now turn to the maybe the implosion. So we talk about the following equation in the second order. We change the variable scalar factor to the z and the curvature perturbation clear to the v. And this gives the following equation by the Fourier transformation. This is just a simple harmonic oscillation, but the frequency is time dependent. For the horizon limit, this is just simple harmonic oscillators because the K inverse is smaller than the Hubble size. But when the horizon case, the T prime of the Z is just similar to the A square I square for the slow rolling inflation condition. And this term becomes dominant in the horizon case, so it has a time dependent frequency equation. Now we'll quantize the sort of this V as a operator. That's the periodic quantization, ladder operators and the canonical conjugate relation. And after that, one can find the solutions of this V K at the K mode at the tau equal to the minus infinity as initial condition, and at the earlier approach before the implications leading the sub-horizon case, so the one can find the limiting solution, and the exact solutions can be obtained. There's additional correction 1 minus I over the K tau from the time dependent frequency. So this is called the boundary derivatives vacuum for the sub-horizon case. And for the super-horizon limit, the frequencies become time dependent, and the VK has a two solutions, tau squares and one of the tau, and the important ones there is a constant one. If one recover the original variables clearly R, then the curvature perturbation clearly R has a constant solution. So now the results that are coming. For the super-horizon case, the curvature perturbation clearly R has oscillation solution, but after the super-horizon, clearly R has a constant solution. So the curvature perturbations that becomes frozen outside the horizon. And by using this result of the KR, one can also define the two-point correlation functions and the power spectrum. PRK and the delta scale RK is a dimensionless quantity. And we know that the solutions of the boundary debris become the equations, the quantities of the V. So the delta scales R dimensionless power spectrum of the curvature perturbation R has the following form: Hubble scales of pi and overall scale. This is a primordial perturbations, which is arising from the impulsion. This can be connected to the observation. One can parameterize this dimensionless power spectrums as amplitude AS and the K with the spectral index NS. This is called the tilt. And also there is higher corrections logarithm. And this amplitude AS is directly related with the CMB and the CMB, the impulations parameters like the slow roll, epsilon, and the potential here. And the spectral index analysis also related with the slow roll parameter epsilon and eta. So the point is here, the impulations potentials gives the density perturbations and related to the observation. Now again the CMB. The CMB, the temperature anisotropies also has the positive effects and the integral success effect, ISW. In the early approaches, during the RD, the gravitational potential powers are the case of the pi does also changes, but in the lifetime approach, the gravitational potential powers are decreased in the dark energy dominant era. So this is a power spectrum of the CMB for the small L to large scale. The horizons are entered RD, but in the large L, the sub-horizons are in MD, so the baryon-acoustic oscillations appears in the large L. For the large L, the scales are small, so still in the MD, so the baryon-acoustic oscillations appear. So I will skip some detail. I spent too much time already. So maybe they're almost. And about the large also there are damping impact already we discussed in the previous video. And the one can obtain the peak baryon-acoustic oscillation peaks latest with the following condition. And this is directly related with the factors R as a relationship between the baryon and the photons energy density. So the point is here that by the CMB, one can extract the informations of some baryon density by using the peak position or peak height of the baryon-acoustic oscillation. So the CMB can be the cosmological parameter. This is the point. Again, the impulsion. Also, similarly, one can calculate the tensor perturbation as we did for the scalar part. All things are same. The seconds of the perturbation for the tensor part, but the TT gauges, there are additional polarization factors, and again the variable V and the Z, and also contours, initial condition, bound David's vacuum, and the solutions with time dependence, frequencies, simple harmonic oscillation. And also similarly, the one can assign the tensor perturbations around this power spectrum and the related to the Hubble horizon, but there are additional factors. So this is the result of the tensor power spectrum. And by using that, one can define the tensor scalarity R as the lattice between the delta H scales or the delta scales, and this is also related to the slow roll parameters epsilon. And by the observations that these are extremely small, less than the 0.06. And also the impulsion can provide the direct observations of the gravitational wave. The quadratic of the H dot gives energy density of the gravitational wave. And the gravitational waves arises from the impulations, has informations of the perturbations and its evolution. So this is plot for the gravitational waves just from the impulsion over the K mode. For the last K, mode is the very small, so don't need to mind by the impulsion. But in the RD and MD, the behavior of the gravitational waves changes. Maybe that will clear sort of that this gravitational wave from the impulsions lightest. But the point is here, the gravitational wave from the impulsions can be calculated by the tensor perturbations, and the shapes is determined by the when each K moves that enter the horizon. So by using the several gravitational sort of probe like as a LIGO with the interferometers or PTI for the long waves lengths with the extra size, and the more large scale cosmological scale can be proved by the CMB over the scale mode. So this is a primordial gravitational wave spectrum from the impulsion. But if the surge particles exist, the amount of the freedom changes, so also the gravitational waves also can changes. The finally we talk about the CMB polarization. Also we talk about it in the other video. Quadrat probes the CMB only can give the polarization state. And by using the optics, there are the Stokes factors from the EX and the EY, the electric field of the photon. One can define the polarization tensor by the compositions of the E and the B mode. Scalar perturbations only gives E mode, but the tensor perturbations that gives both E and the B mode. And already we talk about only the TT CMB power spectrums, but there's other possible EE mode and the BP mode. For the BB mode, the only is derived from the gravitational waves. And because such polarizations are from the quadrat probe, so that this becomes smaller than the TT. There are several behaviors. For example, the TT deals correspond to the EE peak, and the TE has a sign changes, and the B mode only from the gravitational wave. And also there are some advanced topics by for instance with the EB mode, which can be formed by the axion proton coupling. Maybe the final one, the CMB, not the CMB, the impulsions to the test. The scales of the AS, the amplitude 10⁻⁵, and the NS, the spectral index or tilt is 0.97, and the tensor scale latitudes are smaller than 0.06, and these all quantities are related to the impulsions model. And the simple polynomial models already exclude this, and there are some other several models like the Starobinsky impulsion, Higgs impulsions, and alpha attractors. Also, there are some advanced topics, non-Gaussianity, 3-point correlation functions given by spectrum, and the impulsions can be related with such a bispectrum. And there are also some criticisms of the impulsions. They are just impulsion, just a model, but we don't know how can we disprove. And there are also the more extensions beyond the single fields, the slow impulsion. One can also introduce the ultra slow law. If the V prime is extremely small, zeros, then the epsilon is just against very small, but eta can be large, like as the values of the 3. And also one can introduce a multiple field, like as axion impulsion or spark theta field. And also there are also another topics relating to the impulsion, how the standard model particles arise and the thermal passes are. So I talk about the too many topics of the CMB and the impulsion styles as a summary of the cosmology school note. The point is here, there are the CMB power spectrums and temperature and anisotropy, and each mode has a different contributions, and the impulsions there are several model several parameters, and they can resolve the problems of the Big Bang standard model, and these impulsions can provide sort of the advanced primordial perturbations. We talk about the scalars and tensor perturbations, and this directly related with the observational value like the scalar index, amplitude tensor scalar lattice, random lattice with the formulatic relations between the scalar parameters and the potential shape. So already I think there's some topics overlap with the original cosmological perturbation series. And next time I talk about the remaining topics in the cosmological note on the large scale structure, dark matter, and the gravitational waves, but combining all of them. So also the next videos, the topics might be the swap.